All right, so 3-1 and 3-2. Okay, we're going to start by just looking at how can we solve systems of linear equations here. This is a review from Algebra 1, so a lot of this should be familiar, but we need to make sure that we can solve these very, very good. Okay, so just, let's review real quick here. Systems of equations. Okay, what does that mean? It is simply just a set or list of alike equations. Okay. The symbol that we use to group them is like a bracket like this, which you will see right there, okay, in example number 1. Now, how do we find the solution to a system? Okay. The solution to any system is just the values of the variables that make all equations true. Okay? So like for instance, in linear systems, okay, it's a coordinate, it's a point, x and y. So if I were to take whatever coordinate I find, like let's say 3, 1, and I plug it into both the equations, and they are true, then it is a solution to both of those equations, right? It is the overall solution to the system. So we basically say if we're looking at them on a graph, it is going to be the intersection point. Okay, so we're essentially just looking where do these two lines intersect. Okay? So let's take a look at example 1. And we need to understand when do we need to use or solve by graphing. When do we want to solve by graphing? Okay? Most of the time, we really want to graph either when we tell you to, or if you're using like a graphing calculator, to use it to like check your work. Most of the time, graphing, there's a lot of simple mistakes that could be made. So you need to be extremely careful, okay? So let's try, okay? Taking a look at this example here. We're used to writing them or graphing them when they're in the form y equals mx plus b, okay? So if I look at the first one, right, number 1 here, y equals x plus 2, that one's already in that form, and we remember that m is going to always represent your slope, b is always going to represent your y-intercept, okay? So in this case, right, remember that's an invisible 1, so my slope is 1, and my y-intercept is 2. So I'm going to graph number 1 here. Okay. So number 1, we got a y-intercept of 2, and remember a slope of 1 is just a rise of 1. Rise of 1, run of 1, 1 over 1. So up 1, right 1, up 1, right 1, up 1, right 1. Okay, and we need to make sure that when we graph it, okay, we have to attend to precision here. Okay, so like my line's not exactly all that straight there, but make sure that when you graph it, that you use a straight edge. Okay, and make sure that you always label your lines. So this is y equals x plus 2. All right. Now, that's our first equation. Okay? Our second one, if we take a closer look, number 2 here, is not in that form. Right? The second one is 2x plus y equals 5. Okay? But there's nothing that says, right, that we cannot solve for y here and rewrite it. Right? We have to have the ability to solve for any variable. So I'm going to subtract 2x from both sides, and I get y equals negative 2x plus 5. Right, so it is now in that slope-intercept form, so my slope is negative 2, and my y-intercept is a positive 5. Okay, so let's take a quick look. Let's graph it. All right, y-intercept's at a positive 5, so 2, 3, 4, 5. Okay, and remember, if my slope is negative 2, that means that I have a rise of negative 2 or run of 1. Okay, which means simply just we go down 2, right 1. Okay, so down 2, right 1, down 2, right 1. So it's going to look something like this. Okay, so here is the equation 2x plus y equals 5. Right, and I see they intersect at this point located at 1, 3. So I'm saying, okay, the solution to the system here is the point 1, 3. Okay, but how do I know that it is for sure, right? Always make sure, if possible, that you guys check your answer. So check your answer by plugging that point back into the original equation. So we get, let's see here, y equals x plus 2. So 3 equals 1 plus 2. Yep, works for the first one. Okay, and let's double check to see, does it work for the second one? Okay, 2 times 1 plus 3 equals 5. Right? 2 plus 3 equals 5? Yep, it works for that one as well. So 1, 3 is our solution to this system. Okay, and that's how we solve by graphing. Right, but like I said, it's not going to always be the best route. Okay, substitution. Right? There's certain times when we want to use it. All right? At some point, you guys are going to have to make those decisions. When is it probably a good time to use substitution instead of like graphing or elimination? Okay? And more often than not, it's if we see that one of the variables is isolated. Doesn't matter whether it's in the first equation or the second. If we see one that's by itself, okay, then we probably want to use substitution. And the difference is with graphing, it's going to be a little bit more difficult to obtain precise answers, right? Because some of them might intersect at points that are not integers. And that's where substitution and elimination come in, because we can find the exact answers every time. So when I look at the first example here, we don't have a variable isolated, but we can easily rewrite one of those two equations into the form x equals or y equals. And if I look closely, that first equation, okay, x minus y equals 12, I could add y to both sides, and I could get x equals 12 plus y. And then, if we think about it, now I can take everything on this side of my equation, and I can substitute it in for x in our second equation. Okay, so we're going to replace the x in the second equation with 12 plus y, right? We are substituting in. Okay, so here's my equation. 2x plus 3y equals a negative 1. Okay, and we're going to substitute that 12 plus y in for x. So I'm going to use parentheses. Okay, and that's a great reminder that, remember, it's 2 times all of x, right? It's 2 times x. So we need to make sure that we use parentheses every single time so we don't forget that we want to distribute the 2 to both the 12 and the y. Okay, so we get 24 plus 2y plus 3y equals negative 1. Okay, and now if we look closely, we have equations here. Okay, an equation here with just one variable in it, so we can solve for that variable. So we get 24 plus 5y equals a negative 1 when I combine those like terms. And then if we take a closer look and subtract 24 from both sides, I get 5y equals a negative 25. And then to solve for y, we're going to divide both sides by 5. Okay, so we found y. All right, we were able to find y here. Okay, now let's see what happens when we plug it back into the first equation. So x minus y equals 12. I'm going to substitute negative 5 in for y. So be careful here, right? Use parentheses because then it reminds us we're subtracting a negative 5, which turns into x plus 5. Okay? And then if I subtract 5 from both sides, we're going to get x equals positive 7. Okay, so now remember, these are my potential answers. Okay, I'm not 100% sure if they are my actual answers. So what we need to do is now we need to make sure that they are the correct solutions. And the only way to do that is we need to plug them into both of our equations here. Okay, so I'm going to plug it in the first one. X minus y equals 12, right? So let's see, x we found to be 7. 7 minus a negative 5 gives me 7 plus 5, which does equal 12. And then we're going to plug it into the second equation, which is, let's see here, 2x plus 3y equals negative 1. So 2 times 7 plus 3 times negative 5 equals a negative 1. So 14 minus 15 equals negative 1. Yes, that is a true statement. Okay, so we just found that our our solution to the system is when x equals 7 and y equals negative 5. So we could write it as a point. Okay, so that is substitution. Let's take a look at elimination now. All right, when do we want to use elimination? Okay, more often than not, the only time we really use elimination is when they're in the same form, okay? When every variable kind of lines up. So we see our x's line up here, our y's line up, and on the other side of our equation, our constants line up there. So that is essentially when it is in standard form. When both equations are in standard form, that's usually the ideal time that we should probably think about choosing elimination here. Well, you could, with the second equation, maybe subtract 2x from both sides, and you could isolate a variable. But just for practice here, okay, elimination, we need to obviously eliminate one of the variables, okay? And it doesn't matter which variable we choose. In this case, I'm going to look at my y's. Now, remember, this is an invisible 1 in front of the y in our second equation. So if I want to eliminate a positive 3y, I have to have a negative 3y. So what we're going to do is we're going to multiply everything in the second equation by a negative 3. Okay, and the reason we're doing that is because then we can turn that positive 1y into a negative 3y. And when I add a positive 3 and a negative 3, we're going to cancel out and get 0. So let's take a look here. Okay, when we multiply negative 3 times 2x, we get a negative 6x minus 3y, right? And a negative 6 in my second equation. Okay, and using elimination, we're adding together the two equations, right? So if I take a look, 3x plus negative 6x is a negative 3x. And then we accomplished our goal because a positive 3y and a negative 3y eliminate one another, right? They cancel out. And all we're going to be left with is 4 plus negative 6, which is a negative 2. Right? So now we only have one variable left. Divide everything on both sides by negative 3, and we get x is a positive 2/3. Okay, and from here on out, it's the same process that we did with substitution. Now we want to take that 2/3, and we do want to substitute it back into one of our two original equations. Right, so we're going to take that 2/3, plug it in for x here. Okay, so 3 times 2/3 plus 3y equals 4. Okay, 2/3 times 3 is going to give me a positive 2. And when I subtract 2 from both sides, I'm going to get 3y equals a positive 2. And then when I divide, we get y to be also positive 2/3. Okay, so my solution would be 2/3, comma, 2/3 if we're writing it as a point. Okay, and you also can check your answer, plug it back in to both equations, and you'll see that we're going to get the same output. So this is going to be our solution. But if you always want to check, plug it back into both equations, okay? If you're not sure. Okay, so what we're going to do is we're going to take a look at number 4 and number 5, and we're going to discuss, okay, which method should we probably choose? And then what I'm going to do is I'm going to pause the video, and you guys need to pause the video, and we're going to do 4. We're going to go over it, and then I'm going to have you pause for number 5, try it on your own, and then we're going to go over it, okay? So first and foremost, I look at number 4, I see a variable, it's isolated. So I'm probably going to want to use substitution. Okay, so the first thing you always want to decide is which method do you want to use. Okay, if you get to choose, right, any method you choose. Right, and when I say any method, for the most part, let's stick to substitution and elimination here. Okay? All right, and then I look at number 5, and I see, okay, both of these are in the same form. So I probably want to be thinking elimination. Okay, so now that we've discussed, right, okay, first one, probably want to use substitution. Second one, elimination. What I want you to do is I want you to try and pause the video and do number 4. Okay, just number 4. All right, so if we're using substitution here, double check to see if you were able to substitute that negative y minus 12 in for x in your first equation, if you got an output of y equals negative 6 here. Okay, so double check that first, okay, and then after, pause here for a moment, and then plug it back in and see if you can figure out what x is. All right, so after plugging it back into one of the original equations for y, and we find that x is equal to a negative 6. So my solution would be negative 6, negative 6. Now, once again, you can double check to see if it is a solution by plugging that in to both of the equations. All right? Pause the video and let's see if you guys get started on elimination with number 5. Okay, set it up in number 5. Try and eliminate the y. Try and eliminate y in number 5. Okay, set it up. Okay, so if I'm going to try and eliminate y, I'm going to multiply the first equation by 2 because I want to turn that negative 2y into a negative 4y like we did here. So after I multiply everything by 2 in the first equation, okay, I'm going to get a negative 4y and a positive 4y. And when I add those two together, we're going to get our y's to cancel out, and we're going to be left with 10x equals a positive 20 when I add our x's together and add our constants on the other side. So all I need to do is divide both sides by 10, and I get x equals positive 2. Okay? Now plug that into the first equation, the original equation, and see what you guys get for y. Okay, so if I plug positive 2 in for the original equation, we're going to get an output for y to be a positive 1/2. So my solution written as a coordinate would be 2 1/2. Okay, so be careful with those negatives, all right? And remember, once again, you can check your answer if you plug it in to both of the equations and see if we get the same output. Okay, but we're going to look at two special types or special cases that can occur in numbers 6 and 7. All All right, so in number 6 and number 7, okay, both of those kind of line up. So we're going to use elimination for both here. And if I look at number 6, maybe I want to get rid of our x's. So if I want to turn a 6x into an 18x, I'm going to multiply everything by 3 on both sides. So we're going to get 18x minus 3y equals a negative 6. And I'm just going to rewrite my second equation below it. Okay, and when we add those two together, right, I actually see that my x's cancel out, but so do my y's. So if I add everything on the left side of my equation and everything cancels out, that means we're just left with nothing, right? 0. On the right side though, negative 6 plus 4 gives me a negative 2, and we know that 0 is never going to equal a negative 2. Okay, so this is a special case because in this situation we find out that there is no possible solutions, right? This is not true. This is never true, actually. So that always is going to imply that there is no solutions here. Okay, no solutions whatsoever. Okay, if I do the same thing with number 7, let's say I try and eliminate my y's here, okay, a negative 3y, positive 9. I'm going to multiply the second equation by 3, everything by 3. So I'm going to rewrite the first one, okay, and I'm going to get a negative 3x minus 9y equals a negative 21. And when I add those together, well, everything, my x's and y's on the left side of my equation cancel out, right? So we're going to be left with 0 on the left. But this time, 21 plus a negative 21 cancels out, and we're left with 0. And we know 0 is going to always equal 0. So this is always true, right? Or just a true statement. Okay, 0 will always equal 0. So that is going to imply that we're going to have infinitely many solutions, or an infinite amount of solutions here, okay, or all real numbers. Okay? So let's sum everything up from today. Whenever we are trying to solve systems of 2 linear equations, okay, systems of 2 linear equations here, there is always going to be 3 different possibilities. Either we are going to have one possible solution, right? A coordinate, x and y. Okay, and they're going to have 2 lines that are going to intersect at one point, right? Slopes are going to be different. We also could have no solution. Okay? And that's going to always occur when lines are parallel. So anytime we have 2 lines that are parallel to one another, they're never going to intersect, which means that they must have the same slope. But they have different y-intercepts. Okay, and the last possible solution, or the last possible instance that we could have with 2 linear equations, is that there could be infinitely many solutions. Okay, and that's when the lines are the same, right? They just might be written in alternate forms. Okay, and sometimes it might be referred to as all real numbers. Right, so there's infinitely many solutions because, you know, you think about it, I could write x plus y equals 2. An equivalent form, or written form, would just be 2x plus 2y equals 4, right? If I just multiplied that first equation, everything by 2, this is an equivalent form of that equation. Okay?